YouTube as we speak. I will verify that in a second. And redirecting to YouTube. And let's see. Started streaming. Yep, we are live. I've muted my screen. We already have 6 viewers. We have 6 thumbs down. That's awful. How could people do that already? They don't even know how bad this is going to be. Welcome, everybody out there. We are letting the audience trickle in. I am going to ask my guests who have Twitter accounts to tweet out. If you guys can tweet out, Janna, Sara, David, that we are now live on Twitter and Facebook. That would be helpful. We'll let people build up the anticipation coming into this great debate version 2.0, second millennium edition. So welcome everybody. Very thrilled to have so many phenomenal guests joining us today. We have David Spergel, Wendy Freedman, Adam Riess, Janna Levin, Sara Seager, and myself, plus we have Sam Singer and Michael Adler from Wyoming Stargazing Association. So we are really thrilled to have everybody here joining us. We have a lot of people viewing already. And I want to thank all my guests and thank the audience. And tonight's going to be really fun. It's sort of experimental art, and we're going to do our best to make it through. I'm going to send out the actual link to everybody on YouTube. And then we'll get started with some introductions. So as I said, places everybody. And we're going to get started. And if you have a moment, there was a link to register for the giveaways that'll be going on after the live stream ends. We're going to have many, many giveaways of phenomenal signed artifacts from our phenomenal guests. So please do visit the link that I'll put in the chat box in just a second. So let me pin that. Okay, we now have, count them, over 51 people viewing, but that's going to go up. So I want to welcome everybody to the live stream. I want to introduce my friends who have joined me today in this project that sort of conceived a few months ago when I recognized that we were in the 100th anniversary of the so-called Great Debate, which is the famous Curtis-Shapley debate, which solved a little thing or helped to solve a little thing called the size of the universe. So we're joined today. We were going to do some live stargazing. Unfortunately, because of the weather in Wyoming, who would have guessed that in South Central Wyoming in November, there'd be bad weather. But nevertheless, there are usually great opportunities for stargazing. And I want to point your attention to Sam Singer. I'll now highlight him and he can introduce himself and describe the mission of the Wyoming Stargazing Association. And then we'll show some images of their facilities. Samuel, welcome to the live stream. Great debate.
Thanks so much, Brian. Thanks for having me. Wyoming Stargazing is a 501c3 nonprofit organization based in Jackson, Wyoming, as Brian said. And our mission is to inspire and educate through Wyoming's extraordinary skies. We do that through in-person stargazing programs and more recently, virtual stargazing programs, as well as lots of other indoor presentations. So as Brian said, we do have a snowstorm tonight. We've got some great images that we've taken over the past couple of months that we're going to share with you, as well as some cool process color images done by one of our board members, Mike Adler, who is also here with us tonight.
Yes, and that brings me to a description. I'm going to share my slides here. So first of all, I have the panel that I'm going to show up here. And there's the two of us. Let me share my screen. I'm going to share the keynote that we prepared with some images that we're going to be talking over today. So can everybody see that on anybody watching on YouTube? Let us know about that. And by the way, we are monitoring the comments, so please provide live chat comments, etc. So this we're calling the Great Debate version 2.0, and welcome everybody. So the great debate took place in this facility, which is the Smithsonian Institution in Washington, D.C., which looks a little different than it did over 100 years ago when this great debate took place in April 1920. Just to set the scene, it was right after World War II had ended. It's right after the Spanish flu had sort of claimed.
World War I.
Say that again?
World War I.
World War I, sorry, yes. It was unfortunately a precursor to World War II. You see here the headlines of the New York Times. And you also note that the Spanish flu had just barely come to an end, only a few months earlier prior to the Great Debate. And you may wonder, well, what was this Great Debate about? It wasn't a presidential election, although there were many hotly contested election contestants at that time. Warren Harding, the eventual victor, and his vice president, Calvin Coolidge. I like to point out that the administration lasted, little more than some TV seasons last, and that was only about 18 months or so. And so Warren Harding never got to hear the outcome of the Great Debate, which was settled only about 3 years after the actual Great Debate took place. It wasn't settled until 1923. And we'll
Brian,
talk
I'm
about
not sure if your slides are advancing.
Oh, they're not, huh? Okay, let's see here. Let me see. Bring your sharing is paused. Bring your screen to the front. Stop share. All right, what about now? Can you see some?
Mm-hmm.
Okay, good. So this is the remembrance of the events I talked about, Germany surrendering, end of World War I, Warren Harding running with Calvin Coolidge with a song written by Al Jolson. That's pretty funny. And then they ran against James Cox and Franklin D. Roosevelt, who I believe did have a successful campaign many years later. And then this great debate was held, and I think it really inspires us as astronomers that this is really the enduring takeaway from 1920 was that this great debate kind of persists in our memory, and whoever was running for vice president really is lost in history, at least unless you're, Nate Silver or somebody like that. So you see the two gentlemen that we're going to be kind of talking about, Heber Curtis and Harlow Shapley. And we're going to be talking a lot about the telescopes that they used and future telescopes built in some cases by people that are on this very live stream. This is the Hooker telescope in Mount Wilson. And it really harkens back to where do we sit in the universe? And to begin, I want to start with the man that really settled this was Edwin Hubble, but he couldn't really settle whether or not these smudges, these nebulae, were actually in the Milky Way or outside of the Milky Way. This is M51. I think we'll see an image of that from Mike Adler's instruments in just a bit. Here are some sketches. Herschel observed these. And of course, it wasn't until Henrietta Swan Leavitt took images of the Cepheids that we began to discover what it meant to measure distances out beyond the Milky Way galaxy. And of course, I'd be remiss if I tried to explain these data. And I wanted to maybe first start off with Wendy Freedman, who has been known to use a Cepheid or two in her day, to talk about what did Henrietta Swan Leavitt do and why was it so important to discover these mysterious objects called Cepheid variables.
So you're going to go back to Henrietta?
Yeah, that's her, I believe.
Yeah, so in 1908, Henrietta Leavitt, who was working at the Harvard College Observatory, discovered as she was looking at one of the nebulae, the Large Magellanic Cloud, and two of them, the Small Magellanic Cloud, and she found that there were stars in the nebulae. And when she measured how bright those stars were as a function of time, she noticed that the luminosities of the stars changed. They got dim for a while, then they got brighter, then they got dimmer, and they did it in a very characteristic way. And there had been a type of star known as a Cepheid. It had been known for a couple centuries before that from our own galaxy. And she realized that the brightness of the Cepheid stars that she had found had a one-to-one correlation with how fast they changed in their brightness. So here's her, what is now called the period luminosity relation. And actually, recently, it's been named the Leavitt law in recognition of her discovery. So the bottom axis shows the logarithm of the period of variation. These stars tend to vary on timescales of a couple days up to maybe 100 or even greater than 100 days. And then on the y-axis, the luminosity is increasing as you go up. And she's looking at the maximum luminosity of the stars on the top here and the minimum luminosity. Today, we tend to look at the average luminosity. But the uniqueness of these stars, the power of these stars, is that once you realize there is this correlation, if you can measure the absolute or intrinsic luminosity of a Cepheid in, say, our Milky Way galaxy, so its power, its wattage, then you can measure the Cepheids in a nebula, and you can see, is this nebula nearby or is it far away? And so maybe we'll talk about this a little bit more later. You can use geometric parallax, for example, to set the scale in our Milky Way galaxy. And we're getting ahead because Henrietta Leavitt wasn't able to do that. But the power of her discovery is that you go find these stars, they're changing their brightness with time. You measure their periods, you get a sample of them in a galaxy, then you compare them to ones in our own galaxy for which you know the distances. And then just as you look at a lamp post in the distance, we know that things get fainter as they get farther away, and they do that in a precise way, falls off as the square of the distance from us. But Cepheids remain one of the most accurate and powerful ways that astronomers have today to measure the distances to galaxies. And that's what Edwin Hubble did. He found these Cepheids in a few galaxies, and now we know as our local group nearby galaxies, including the Andromeda galaxy. And he was able to show that these stars in these nebulae, based on the Cepheid variables, were much farther than our own galaxy. So they weren't actually regions of star formation in the galaxy, which was part of the debate in the Shapley-Curtis debate. So we use them today. That was one of the main goals of the Hubble Space Telescope, was to be able to accurately use Cepheids to measure the distance scale of the universe, which I'm sure we'll get into more later on in the discussion.
Yeah, thank you very much. I love the way that in old days, people could make plots and not label the axes, or label the axes incorrectly. So here's a law, Leavitt's law. So here's here is Hubble's famous diagram. I mean, Adam, David, you guys can chime in here. If one of your students turned in a plot like this with incorrect units, with no error bars, what kind of grade would she expect to get?
She'd get it right. He got it wrong.
Brian, I wish that that was only errors that people made in plots back then. I can show you some papers from some of our colleagues, some famous ones.
Oh,
I don't know. I hope I look past the wrong labels and see the profoundness of the result.
Yeah. So, Adam, let's go back to that time. I mean, you're a little older than I am, but not that old. And when Hubble discovered this famous Cepheid in the outskirts, I believe it's on this side here, if you can see my screen, he immediately crossed off the sign that he had made for a nova and replaced it with Ver. Why is this so important to get one single star? And actually, yeah, I've never known. How did he know this was not a foreground star? I mean, what gave him the confidence?
Yes. Well, that's a great, those are all good questions. So people knew about what we would call novae or even supernovae, which are, they're sort of one-time deals. They get bright, they get faint, that's it. So Hubble was observing this star, thinking initially that it may be a nova or a variable, but he saw it start to repeat. And so he crossed that off and realized, oh, this is a variable star, not one of these novae. And then he could, as Wendy described, associate that with more nearby versions, compare their brightnesses, and determine that the Milky Way was, that Andromeda truly was far away. Then to determine, as you said, how do you know it was in Andromeda? He looked off the field. He looked away and noticed that he was seeing lots of these Cepheid variables superimposed on Andromeda and not away from Andromeda. And so he realized, okay, these are certainly in Andromeda.
And then at the center of these massive, beautiful spiral nebulae, as they used to be known, and many of them have a heart of darkness, a black hole. And today we're joined with Janna Levin, who is to be congratulated on the publication day of her fourth book entitled Black Hole Survival Guide. Now, Janna, if we take a journey to the center of Andromeda, will we be safe from a black hole, or will we possibly meet a type of doom that none of us can imagine, known as spaghettification?
Well, there's definitely a black hole, supermassive black hole at the center of Andromeda. It's bigger than ours, and we're on a collision course with Andromeda, which is interesting. There's sort of a competition between whether our star will distend and die or will collide with Andromeda. We'll probably collide. I don't know. Somebody remind me which one happens first. But we're definitely on this beautiful collision course with Andromeda, and so the expectation is that the entire solar system will stay intact as this happens. They'll pass through each other because the stars are actually quite sparse. So they'll pass through each other and then they'll come back, and they'll do it a few times before eventually they coalesce and our black holes merge. And our whole solar system hopefully will stay intact and just be on some peculiar orbit around this new supermassive black hole.
And again, to look for Janna's new book. We did an interview early this morning on publication day, just about the book and just about Janna's work in black holes. So we see here, I think this is the negative of it. I've actually had the actual plate in my sweaty hands. They don't let you do that anymore, but I knew one of the archivists. And you can almost feel the palpable
excitement. When I was director, we still did that.
If you did that, right. Okay. Well, I didn't drop it, Wendy. Don't worry. Now, Wendy, when you see these things like these light curve that's superimposed here, this is called V1 in Andromeda. So there's a Cepheid there. It looks pretty good, but I mean, could you, can you say something about the challenges of modern day extrapolation? It seems like Henrietta Swan-Leavitt was heroic, as was Hubble in a certain sense, in trusting the data, to really make this far-flung association that these objects are at great distances, and then later that they're receding at great velocities. And we'll get into that in a moment. But how well do we know how much has the improvement has there been in both Cepheids and other distance ladder techniques?
Yeah. So if you look at these data and you think, here are Cepheids, which are faint against the background of Andromeda, right? So it's hard to make these measurements very accurately, because what you're trying to do is measure a single star, how bright it is, but you have to contend with the fact that it's in the disk of the galaxy. And then when you think back to what Hubble and Leavitt were dealing with at that time, the detectors that we had were photographic plates. They weren't electronic detectors, the charge coupled devices that we have today, that we all have in our cell phones, similar technology, but they were emulsions on a glass plate. So this original of Hubble's, and photographic plates were very inefficient. Only 1% of the light coming from the distant galaxies lands on your photographic emulsion. But worse than that, there wasn't a one-to-one correspondence between the brightness and what you measured on your photographic plate. So they had a lot of issues to contend with, including the fact that they weren't able to correct for the presence of interstellar dust. So that's dust that's expelled from the atmospheres of stars. It absorbs the light that's coming from your Cepheids and it scatters it, so it makes it look fainter. And then you have the Earth's atmosphere to contend with, which is why the Hubble Space Telescope made such a big difference. So yes, these measurements were very, very difficult. And in fact, Hubble got it wrong by about a factor of 7. The original value for the Hubble constant that he measured, so the Hubble constant being the slope of the relation that you showed, I don't know if you want to go back to that, between velocity and distance. And so I'm not sure we pointed out to viewers who weren't familiar with this plot before, but what we were referring to, what Hubble got wrong, is that the units of velocity he put in kilometers rather than kilometers per second. And so you can see there's a lot of scatter in this plot. It's quite amazing that the implications of this result. So what he found is that the greater the velocity of a galaxy, the farther away the galaxy is. And so you could see there's quite a bit of scatter along that line, and that's because it was hard to measure the distances. But there's no question that there is a correlation, and the implications of that correlation were enormous. It's what eventually what we came to realize implied, if you took it together with Einstein's general theory of relativity that he had developed in 1915, if a galaxy is far away, it's moving faster from us, or appears to be moving faster from us. And that would imply that there was a time in the past when galaxies, in fact, all matter was closer together, denser, hotter, and what eventually led to our picture of a Big Bang universe. So the implications of these results were enormous, even though he got it wrong by about a factor of 7.
And David, you pointed out in publications of the National Academy of Sciences over 2 decades ago that, one of the reasons was that the reddening of dust combined with the lack of sensitivity of the photographic emulsions made for this, as one of our former presidents used to say, misunderestimation of the actual value of the Hubble constant. Can you say something about what was the actual resolution that caused Hubble to get it wrong by a factor of 7? Again, I'm not that great an astronomer, but I'd like to think I could get, close to an order of magnitude. Why did he get it wrong by so much? And why should we have any confidence in these astronomers who are so graciously joining us today, that they now know what they're doing to the sub-percent level?
Well, I think it's actually, before I get to that, I wanted to actually step back and look at what went wrong with Shapley, right? Because this was the great debate.
Yeah.
And Shapley had this argument that Andromeda was right near us. And Shapley's arguments were actually pretty good, right? I sometimes think we look at the losers in these debates, or we look at, Hubble and say, how could they get that wrong? But these were really good scientists.
Yeah. And
sometimes one has an incomplete picture and you're drawn to wrong conclusions. So one of the things he saw, and this ties into something we'll, I think, touch on later, is he saw this, there was the observation of this explosion, S Andromedae, in the center. And it was so bright, so 10,000 times brighter than, if you assumed Andromeda was far away, it would be 10,000 times brighter than the novae we saw in our galaxy. It was one of 2 possibilities. He assumed the simplest one. It was like other objects we saw, and Andromeda was close. We later learned it wasn't a novae, it was a supernovae, a whole different class of objects, one that Adam and others studied in detail, and that this new kind of explosion, the reason it was so bright was that it was just something they'd never seen before. And the second mistake was an observational error made by a very capable astronomer named von Manen, who thought he had measured the rotation of Andromeda, that the whole image that you see behind me, behind you on the screen, was rotating pretty rapidly. And that they thought they had seen some of the stars, those spots, which we now know to not a lot of these bright things are actually star-forming regions in this image here, appeared to be rotating. And I think a lesson from the debate was many people felt that, Curtis ended up being right. It was Shapley who had the best arguments and won the debate. And as you noted, it was only later when Hubble's data came in on Cepheids where things clarified. And
so, I want to turn to the Hubble Space Telescope, but before we do, we should talk about Hubble himself, the telescope's namesake, who was reputed to have wanted to have become a lawyer, and actually went to Oxford, I believe, to become a lawyer. And he actually went through with it because his dad really wanted him desperately to practice law. And then his dad died, I think, in 1913. And he's reputed to say, upon quitting the law profession, and I know there's many lawyers listening out there, but he's reputed to say, I'd rather be a second-rate astronomer than a first-rate lawyer. He certainly turned out to be a first-rate astronomer. And I'm only, sort of teasing. It's funny that he didn't practice law, but he has a law named after him, and he has He has a telescope named after him as well. And I want to talk about that with Adam. There's a picture of it sitting behind Wendy, and I'm going to put that also on my presentation now. Adam, can you talk about the work that you do with the Hubble Space Telescope? And then I want to talk about the TESS instrument that Sara led, as well as telescopes in space get above the atmosphere. Why is that so important if we're still discussing Hubble's data taken from ground zero, from outside of Los Angeles, I always point out, pre-smog? Why is it so important to get above the Earth's atmosphere?
Sure. Well, if you've ever sat in a swimming pool and looked out at, somebody, you notice it's very difficult to see them well, to count how many fingers they're holding up, something like that. And that's the problem we have down on the ground. When we use telescopes, we're sitting beneath an ocean of air above us that blurs the images. When 2 points of light that are close together come to us, they can often merge as they pass through our atmosphere. And so we don't get these very sharp images that we need. And as was described, in order to figure out how far away galaxies are, we need to resolve or recognize individual stars in those galaxies, which is very difficult to do from the ground. Now, in the case of Andromeda, it happens to be the nearest galaxy, and so that gives you a better chance to resolve individual stars. But as we find ourselves wanting to measure much greater distances, we need to be able to resolve individual stars in much more distant galaxies. So like looking at your friend who's holding up 3 fingers while you're under the pool and your friend's very far away, it gets harder and harder. So there was the clever idea in the 1940s, not realized until around 1990, to launch a telescope up into space, sitting above this ocean of air, to get the pristine kind of resolution you can get from a telescope when the light is not blurred from the atmosphere. And so with this telescope, it is possible to pick out these individual Cepheid variables that Wendy described, but much further away. I would say maybe 40 or 50 times further away than Hubble did from the ground. And if we can look out further and measure greater distances, we can reach out to some of these galaxies that also hosted one of these exploding stars that David mentioned appeared in Andromeda in 1885, a supernova. Now, a Cepheid variable is a very luminous star. It's a supergiant star. It's 100,000 times as luminous as our sun, and so we can see them very far away. But a supernova can be as bright as 5 to 10 billion times the luminosity of the sun. And so if we use geometric parallax to figure out how luminous a Cepheid is, we can then observe a Cepheid in a galaxy that hosted a type 1a supernova and figure out how luminous the supernova is. And then we can see lots of supernovae well out into the expanding universe and use that to calibrate how fast the universe is expanding today.
Now, getting a telescope into space is no mean feat. And there's one of us, at least here, Sara Seager, professor at MIT, author of one of the books we're giving away. So I want to remind people in the comments, I've got a link to sign up so you can be eligible to win both books by Professor Sara Seager, Professor Janna Levin, her newest book, signed copies. Some guy named Brian Keating has a book that you can get as well, plus signed papers by Wendy Freedman on the key project done by the Hubble Space Telescope, which we'll get back to in a bit, and also by none other than Adam Riess, the paper that brought home some Swedish gold. It's not showing up super well. Anyway, sign up in the link. I'll put another link to it. Sara, what's it like before a telescope launches on a SpaceX rocket? Talk us through the emotions that you feel and then what the mission was about.
Well, first of all, it's always a blast. It's always fun to go down to Florida. And what's so great about the mission when you're waiting for it to launch is you see all of your friends and colleagues, some you haven't seen for many years, at the hotel, at the beach. Everyone's waiting for that really special launch day. For the TESS mission, and typically if you're on the formal launch party, you go in a bus at NASA and drive to a site on NASA property. And just as the bus was pulling in, we get an announcement. We're turning back now. It's not going to launch at the moment. So then you wait because the team has to figure out what went wrong, why it's not launching. Yes, and so we had a couple of extra days in Florida. And then you go to the launch and it's amazing, but the whole mission, everything you've worked on for so long, and I wasn't working on TESS as long as some other people, but it's all up there in that tiny top of that fairing. and kind of top of that rocket in the fairing, and you're just kind of keeping your fingers crossed. But I wasn't so nervous because you're just sort of caught up in watching the rocket, watching it launch, listening to the loudspeaker, the countdown, everything. And then it goes in the sky, and it's just one of the most beautiful, like incredible things ever. I hope you all get to see a launch. You know, when we get back to travel normal, new normal, anyone, you can see a launch. You have to pay like $50 or something, but anything that happens to be launching when you're there, you can do the official launch, but you don't even need to do that. Sometimes there's a better view along the road or at the beach, actually. So that was the mission. Then it's not just, that's not the nerve-wracking part, but once you turn everything on, you know, you want to make sure it actually works properly. And yeah, it turns out there's sort of this huge history that pretty much everything that you turn on has some kind of problem. But no one tells you. It's sort of hush hush and secret. So there's no like lessons learned list you can go to. But as Adam and others were saying, you know, above the blurring effects of Earth's atmosphere, it's just incredible. And the TESS mission and, you know, Kepler before it can do incredibly precise photometry, brightness measurements as a function of time. But TESS too, it's not just that on Earth that's bad for us, for astronomy, for exoplanets. It's the day-night we have here on Earth. You know, like I'm sure you love daytime, right, Brian? You want to wake up and have day, and you want to go to sleep and have night, but that's bad for exoplanets because the transits get chopped up. It ruins your so-called visibility function of trying to find periodic events. So TESS is in a really brand new, unique orbit. It orbits Earth in resonance with the moon. It has a 2-week orbit about, and it goes out to half the distance to the moon. And then it comes back and it keeps orbiting. It's just so that when TESS is at its furthest point from Earth, the moon is on one side. And then when TESS goes back to that furthest point, the moon is exactly on the opposite side. And the moon is actually stabilizing the orbit, allowing TESS to look at like a continuous night sky for nearly 2 weeks at a time. So yeah, the TESS mission is amazing. I just want to say one more thing.
Yeah.
I thought you were going to ask me, what is it like to find planets? So
I'm about to do that.
Truly, it's the most amazing thing ever to find a new planet. And it kind of is. And I hate to kind of say this out loud, but like any job, it gets a little tedious, let's say. Like it's crazy to say that, but you know, it's sort of over and over again, same. And every month though, it's pretty amazing that the TESS mission finds about 100 new planet candidates. So not actual planets, but 100 new potential worlds. It's quite a mission.
And one of the ways you do it, I'm showing on the screen now, I think it should be visible, is through eclipse of planets that have atmospheres. And of course, you and your team made some news really in the last month with an announcement of evidence for the production of phosphine in the planet Venus's atmosphere. And I wonder if you can comment a little bit on that, just first describe what the discovery was and what the current status is. I understand there is a little controversy surrounding it currently.
Sure. Okay, so we've switched topics completely now.
Yes. I know.
One of the reasons
I don't have too much time with you guys. I want to make sure I get.
All right, so we switched topics. We're going to drop exoplanets now, and let's say, just for a bit of background, one of my main research areas is thinking about what kind of gases could we find on exoplanets in the future when we can study small rocky planet atmospheres. And one of the gases my team came across was phosphine. It sounds incredibly obscure. It's associated with life on Earth in oxygen-free environments. And it's not made any other way on this planet, except for us humans make it and bacteria almost certainly make it. So while my team had worked on this and put out a few papers, across the pond out in the UK, Professor Jane Greaves independently had realized that phosphine is a good biosignature gas. And she had purposely set out to look for phosphine on Venus, and hence a mutual contact connected our two teams, and we chipped in to help Professor Jane Greaves with analysis, with an interpretation of what she found. So the team announced the detection of phosphine on Venus a couple months ago, and it was based on 2 different telescopes. It's a radio telescope. It's the James Clerk Maxwell Telescope in Hawaii and the ALMA Observatory in Chile. Now, we saw the same feature in 2 different telescopes, but Venus being very bright and spatially resolved. By the way, like, would you ever point Hubble at Venus?
Okay.
Adam,
Wendy, would you?
Yeah, see, no, it's too bright. It's so bright.
The shadow.
Okay, so I made them laugh, but it's hard to observe really bright things. It sounds ironic, doesn't it? Like, wow, I mean, it's hard to observe bright things, and it's hard to look for tiny signals. And by the way, spatially resolved things are also challenging. So it's a hard thing all around. Now in science, in most of these facilities, there's two things I want to say, including about Hubble, but in our big national, international facilities, there's two things that are key here. One is that the data is made public, so everyone can use it themselves. And the second thing, and this includes TESS as well, is we put out calibrated data for the users. So I don't know if Adam or Wendy, do you use the raw Hubble data or calibrated data?
Sometimes one or the other.
Okay, so with TESS, I don't think with TESS we give both the raw and calibrated, but it's not detrended. So there's a lot of terms floating around here. There's sort of a basic calibration that's often done by the facility. And then there's the detrending, the further data analysis you do on your own. So thanks to this intense scrutiny, ALMA, the observatory, found a problem with the way they calibrated the data. Okay, so all the teams that have used the public data, almost all but one, also use the calibrated data. They didn't look at the raw data. So most of those, you can ignore them for now. This is a rapidly evolving situation. So we use the calibrated data. We had ALMA observers, ALMA data scientists on our team. And it had to do with how they use their calibrating object. I'm not going to go into too much detail here because we want to get to some other topics.
Yeah, we did a podcast also. I'll point you viewers to my channel from
but that should include all this latest. Yeah, they can have the background there.
But hopefully you'll come back on the podcast.
So it turns out that when ALMA's releasing the new public data that is like reprocessed is, I think, tomorrow. And so we'll have all the teams can go back to BAT to look at this calibrated data. So yeah, a few people looked at the ALMA data again, didn't see phosphine, but it's an evolving situation. Now, the thing I want to leave all of you with though, because it will take some time for this to play out, is because of our phosphine detection, a team of people went back to look at the Pioneer Venus data. And we hadn't talked about this on our podcast. And Pioneer Venus was a mission from the United States to Venus in the late 1970s that included different probes. And one of these probes had a special gas mass spectrometer on it. And when people went back and looked at this data, they actually, believe it or not, found quite compelling evidence for phosphine. And they found this neutral gas mass spectrometer ionizes the gases, whatever comes in gets ionized. And then it's subject to a magnetic field, which eventually, depending on the path of the ion fragment, can tell the mass and the charge. And so they found a bunch of phosphine fragments, including phosphorus ion, which there's nothing else it can be strongly associated with except for phosphine gas. So yeah, the mystery is out there. This could be a debate, not right away, because we've got to let things settle. But with ALMA, JCMT, and Pioneer Venus now, there's three different things to keep track of for you.
Sarah, what about the other telescopes data? Not ALMA, but Maxwell?
Yeah, so one of the teams that re-looked at that data found the signal and then said, well, it's not phosphine, it's a contaminant. There's only one other possible thing it could be, which is a line of sulfur dioxide, because Venus does, this is for like the non-planetary people, there is a lot of sulfur dioxide, but they had to invoke like a huge amount of sulfur dioxide in order to be able to match that line.
And Adam, can you talk about the challenges of doing calibration? You were responsible for calibrating Hubble for some of the work that you did, and then what does it mean, first of all, to calibrate an astronomical telescope? Don't you just get it from Amazon and go to work?
No, it turns out there's no there's no instruction manual, and you do have to calibrate it. So there are astronomers who work at a place called the Space Telescope Science Institute, which is sort of the headquarters for the Hubble Space Telescope. They run the process of receiving proposals from astronomers, what they would like to observe, awarding time, making those observations. But they also hold back maybe 10 or 15% of the observatory's time to obtain calibrations. And calibrations are in some ways very boring, but they're very essential observations to be able to really make quantitative sense of the images you get. So it usually involves observing certain kinds of stars. Maybe you know their brightness ahead of time, and so you calibrate the telescope. Maybe you observe those stars over the course of 30 years for Hubble and see if the detectors on the Hubble Space Telescope are decaying or changing, if the field of view is distorting, if all the pixels are equally sensitive, or if they're changing over time. So it's a lot of, I would say sort of boring but critical measurements, so that at the end of the day, when you apply these calibrations, you get these very pristine images that you can also do science with. You can also look at the brightness of a star and know, how many watts you're actually getting from that. So you could compare it to other stars.
I wouldn't say that you and Wendy are competitors in a certain sense, but Wendy, can you talk a little bit about the Hubble Space Telescope key project to measure the Hubble constant, this paper that we're going to give away a signed copy of that you graciously provided? What does it rely on? Is it doing imaging? Is it really relying on these calibrations that your competitor, I mean, could Adam sneak something in there to make you get a different result? Just kidding, he would never do that.
So we were looking at Hubble's data early on. There was quite a time where when we made these measurements of distances to galaxies, we weren't getting them right. And you were asking about that earlier. And so Hubble got this value of 500 for the Hubble constant. And then in the 1950s, that came down by about a factor of 2. And then it settled into a regime where some astronomers were saying it was 100 and others were saying it was 50. Now that's a factor of 2 uncertainty. We didn't know the scale size of the universe to better than a factor of 2. And that persisted for decades. And it, in fact, was one of the motivations for building the Hubble Space Telescope. And it is, in fact, the project that led to deciding the final size of the primary mirror. It is that when the telescope mirror, the telescope was being descoped, it was originally supposed to be larger than the 100 inches that it ended up. It was a 2.4 meter telescope. And that was set by the ability to detect Cepheids in a nearby cluster called the Virgo cluster. And so when Hubble was first flown, there was a concern that the time would be divided up into tiny little pieces because every astronomer had been waiting for this telescope for decades. And so there were key projects that were set up. There was a peer review committee that decided what were the most important projects that Hubble and only Hubble could do. And measuring the distance scale was the primary project. And so our group competed for, got awarded the time on the Hubble Space Telescope to try and resolve this factor of 2 debate. And so the way we went about it was to use these same Cepheid stars that Edwin Hubble had used based on the discovery by Henrietta Swan Leavitt. And we measured the distances to about 24 galaxies for which we could make very accurate measurements using Cepheids and tie into other methods like the type 1a supernovae that Adam mentioned that take you out farther into the Hubble flow. And we were able to resolve the discrepancy. We got above the Earth's atmosphere. We were able to make corrections for dust. We weren't using photographic plates any longer. And we had many ways of measuring the distances independently. So you were asking, how did Hubble get it wrong? There were about 4 reasons why it was really wrong. And largely it was the photographic photometry and the reddening. But we were able to correct for that. So we got a value of the Hubble constant of 72. Now, today, so I've worked on Cepheids for a great deal of my career, I know, and love them. But what keeps me up awake is that there could be other kinds of what we term systematic errors. That is, there's some kinds of errors. If you make a measurement over and over and over, sometimes you'll get too high, sometimes too low, but you can average over those. And the more times you make the measurement, the better your average becomes. But there are others that are systematic in the sense, for example, dust will only make your Cepheid look fainter. It's never going to make it look brighter. And so that's going to take you in one direction or another. And so that's one thing I've spent a lot of my career on is trying to devise methods for correcting for dust. And we were able to do that and overcome this problem. So one of the things, as we're approaching now the need for higher and higher accuracy, what we did with the key project is we measured a Hubble constant to a 10% accuracy. So we solved the factor of 2 problem. And then Adam and others in the last couple decades have been bringing down the uncertainty with time. But now the need for even higher accuracy is upon us because we have other means of estimating the Hubble constant in the early universe, which I assume we'll talk about in a little bit. And so we have a need for even higher accuracy. So one of the things that I've been doing with my group is to use a different kind of star than a Cepheid. These are stars that are fainter than Cepheids, they're older than Cepheids, they're red giant branch stars. And the interesting thing about these stars, the unique property that they have, is they achieve a certain luminosity And then there's a fundamental physics limit. They then become much fainter, and they cut off. They don't ever climb higher than a given luminosity. So they're almost a perfect standard candle. We use that term. And the different in the sense than the supernovae or the Cepheids that are standardizable. They have a luminosity that's constant. And you can see them, Brian showing here in the top panel. The white squares are the fields that we're observing with Hubble. So again, we're using the Hubble Space Telescope, and we're out in the halos of these galaxies. So unlike the Cepheids that are in the disk, the giant branch stars, they also occur in the disk, but they're easier to measure in the halos, and we can make the measurements more accurately. And you can see down below, so I'm looking now, it is harder to see in the image, but they're individual stars in the circles. Yeah, you can see some of them. So they're not crowded by the stars in the disk, and we can make these measurements really quite accurately. So on the left, you can see the stars in the circles there. Yeah. So they're very simple, and both from a physical standpoint and also from a measurement standpoint. So we've been recently measuring the distances in the same way as we do for Cepheids in nearby galaxies using the Hubble Space Telescope. We calibrate these stars, say with geometric parallaxes nearby. We measure the tip of the red giant branch in galaxies that also have type 1a supernovae, and then we tie into supernovae that are much more distant. And so the interesting dilemma that we find ourselves in now is that what you measure for the Hubble constant based on these local determinations, that is measurements of stars in the local universe, when we compare those to what astronomers are measuring based on temperature fluctuations in the background radiation from the Big Bang, if you use what we now call our standard cosmological model to fit the data in the early universe, you can infer what the expansion rate would be today. And when we compare that to what we're getting from the Cepheids or the tip of the red giant branch, that value from high redshift is lower. The Hubble constant is about 67, whereas it's maybe 70 or even 74 locally. So the dilemma before us is this a significant difference? So if we look at the history, there have been a lot of uncertainties in the Hubble constant, and the answer has been there have been systematic errors we didn't yet understand, and when we corrected for them, we had a better measurement. So are there still systematics that we don't understand? Or is this a real difference, which would be the most exciting outcome? Because what it could mean is that we are learning something about the early universe, and the model, standard cosmological model, could have gaps in it. We may be learning about new physics in the early universe. So that's what makes this an exciting problem. It's not yet a solved problem, and in a sense, it may leave us back where Shapley and Curtis were. Maybe some things are right, some things are wrong, but we don't know yet where those are. We're at the forefront, and it's hard to see. It's very easy to see in hindsight.
So,
but it's David, exciting.
Yeah, David's gone on.
What's that?
I was just saying, David's gone on record in a sworn affidavit that he thinks that there could be systematics lurking. And first of all, I want to ask David to explain what is the difference between the early universe cosmology measurements that you made with your team on WMAP and ACT and other instruments, and Planck has now corroborated, and the late time, and why they differ by the so-called 5 sigma tension that has gripped the field. Why is this important? Why are these measurements so discrepant? And if you had to bet Janna Levin's pet ferret's life on the resolution, what would it be?
Well, the way we measure the Hubble constant indirectly in the early universe. What we're actually measuring in many ways is the size of the universe, which is related to the Hubble constant, or the distance really out to redshift of 1100, out distance we're looking at when we look at the microwave background. When we look at the microwave background, we're seeing a pattern of hot and cold spots. And there's a characteristic size we see set by the distance a sound wave can move. So nature is basically holding up a ruler to us, and we know how the length of the ruler, we think if we understand the physics, we think we understand the length of the ruler. And then by measuring the size of the hot and cold spots, we can infer the size of the universe. And from that, if we have the right cosmological model, predict what the Hubble constant should be. Now, when we made the measurements with WMAP over a decade ago, and that's a satellite I was involved in launching, we got a value of around 70. And with the error bars large enough, that was very consistent with the measurements that Wendy Freedman and her team made. And we really had a pretty consistent cosmology. On the microwave background side, there's been a lot of progress since then. One big step forward was the Planck experiment, European-led experiment with significant components in the US that mapped the sky at even higher sensitivity. They got values of around 67 or 68. There's WMAP. So completely consistent with the WMAP numbers and the uncertainties, but now with smaller error bars and a smaller value. And that's something we've now been able to check in a number of different ways. So our measurements from Chile with the ACT telescope provide an independent way of measuring the Hubble constant from the microwave background, the size of the universe. And again, we get a value bang on the Planck measurements, and we combine WMAP and ACT, completely independent measurements from Planck, we get a very consistent set of numbers. So I think from the microwave background, I think we're unlikely to have systematic errors because we've got independent measurements making very similar measurements. Now,
sorry, David.
Numbers. Now, what has changed since then, since this plot, is there's been a reassessment of the holy cow measurements and the holy cow values, which this is based on gravitational lensing, another technique we haven't talked about. But that value is now shifted down and is very consistent with the Planck measurement. It's really kind of bang on.
I'll debate that a little bit.
Yeah, let's hear it.
Well, but that's what the people who wrote the paper said. There are really, I think, a couple possibilities in terms of explanations. The most exciting one is that this is pointing to new physics. One piece of potential new physics that I've worked on, a lot of people are interested in, is the notion that we've miscalibrated the ruler. That that there's physics going on in the early universe, things happening back in the first, say, 100,000 years of the history of the universe, that we have not properly included in our model. It could be dark energy behaving in interesting ways at early times. It could be interesting new physics for neutrinos. There's a lot of ideas that people have been developed that would recalibrate the distance ladder and perhaps bring things into better agreement. That would be the most exciting possibility. The most mundane one, but still important, would be that there's something we're missing in our understanding of Cepheids. That's happened before, and Wendy could say more about this, but her measurements with the tip of the red giant branch, I think, have turned out to be a local measurement consistent with the Planck and WMAP and ACT, the CMB measurements, the Hubble constant.
Yeah, and those are holding up with time too. So we have a couple more measurements that we're just finishing up, and that calibration is holding up.
And Adam, you wanted to
discuss I was going to say that in terms of systematics, in the past, people have thought of specific systematics that could involve Cepheids, like reddening or chemical effects. And so the generation of measurements that I've worked on, the SHOES team, specifically addressed those by making observations in the near infrared to sort of look through the dust, and also by using the same telescope to calibrate the Cepheids and look at the more distant Cepheids, so that flux calibration, which we talked about earlier, drops out, and by looking in the near infrared where chemical abundance effects are mitigated. And so what we've seen really, and it's not just the tip of the red giant branch or the Cepheids, but there are surface brightness fluctuations, there are masers, there are Miras, There's Tully-Fisher. These are all different methods we use. And, you know, if you look at the sort of range of local measurements, it ranges from about 70 to 75. But that full range is above what David was saying. The full range that we see from the early universe is really about 67 to 69. The mention of the lensing measurements, by relaxing certain assumptions they made about the mass profiles, they actually become quite unconstraining, which is sort of neither informative about the early universe or the late universe. And so, you know, we're in this position now where we're trying to figure out, okay, is there an error, but is it an error in theory where we are not understanding the model of our universe so that we can connect the early to the late, or is it an error in measurements, as people have described a systematic error? And, you know, we're at the point now, the measurements are so good, I would say, on both ends, the early and the late side, that we're sort of getting past the point where people can sort of wave their arms and say, oh, new physics, or oh, systematic errors. And what we actually need now are specific ideas of how, let's say, a change in the cosmological model could match the observation, so that we can test that, because it's very difficult to come up with an idea that's consistent with the data. And likewise, when people suggest systematic errors, at this point, we need a specific mechanism for how such a systematic error could be consistent with the various measurements we've seen in the local universe, and yet explain the tension we see with the early universe. And so, you know, it's interesting to ask people, you know, what do you think? What is your gut feeling? But I'm more interested at this point in specific ideas that can be tested, because, you know, that's how we always make progress in science, is with, you know, specific hypotheses that make predictions, really, so that we can go out and test those.
I mean, Adam, I disagree
that
with
he
the
said,
assessment of the lensing measurements. The value they quote is 67 plus or minus 4. That's the same kind of errors that most of those results you had in that plot quote.
Right. My understanding was that they had multiple ways, but they're within 2 sigma consistent now with both the local.
Your central value is bang on the CMB value. And they had what they identified as a problem is something that many of us have talked about when we've looked at the previous work, which is this lens sheet degeneracy. The fact that you don't know how much mass, what the mass distribution is around the lenses that they use. And what they've done is get velocity measurements to calibrate that. And with that, they've got a measurement that now seems consistent. That doesn't mean that's the definitive measurement, but I think it's now the plot that we're being shown right now is a little, I would argue, is a bit, today was fine in 2018, but in 2020, and this shows how things progress, is now a little misleading. The 2020 data for that holy cow value, when they properly account for the uncertainties in mass distribution, shifts down to 67.4.
Yeah, I'm just pulling up their paper
I
now.
point out that the
74 plus or minus 5 and 67 plus or minus 4. I guess they have 2 different ways of doing it, but I would agree that it's become unconstraining now. I don't think it particularly answers the question.
Yeah, I think
Wendy, sorry, you were saying something, Wendy?
Yeah, just to add, so the Carnegie measurements that are referred to here, I just want to note that they're based on the Riess et al. Cepheid distances too. So if that proves to be an issue, those would be there. And the tip of the red giant branch that we have land just below 70. So I just agree with David's point that both it's out of date, but it also you have to be careful what is calibrating where, and the holy cow measurements made an assumption which landed them on the high end, but when you get data that can actually constrain the mass distribution, it moved and the uncertainties went up. So I think we're in play here now, and we just don't know where it's going to land, but it's not as simple as saying everything lands on one side or the other.
Janna, I just want to ask you a question from the audience to speak. I know you have to break off pretty soon.
Sorry, I do, yeah. But,
it's okay. They want to know if there's any in the holy cow results that rely sort of on the gravitational lensing, which is a consequence of Einstein's theory of general relativity. Is there a role that black holes could play in the resolution, either primordial black holes that you talk about in Black Hole Survival Guide or other black holes? in the resolution of the Hubble tension, or is it just completely not relevant?
Well, I love that somebody's trying to drag me into the conversation, but I think to a large extent it's really not relevant. But I'm going to take this opportunity of having a minute just to mention how interesting it is that Hubble lobbied to try to get astrophysics considered for the Nobel Prize. I think he was well aware of the significance of what he was doing, but astrophysics was not considered under the Physics Nobel Prize for decades afterwards. And I think it's also really relevant for people to realize that at the time that Einstein was working and that his friend writes him a letter from the Russian front to propose this thing that we now call black holes, Einstein did not know there were other galaxies out there. I mean, that's just tremendous in 1916. And so for Hubble to just have that realization that these objects are outside of us, it's why you started this whole thread with all these brilliant people on this call, is because, our concepts went from this to like, whoa, right? Suddenly the universe was bigger than that. So I wanted just to mention that piece of history because I think that's quite interesting. I don't think it was until, and I'm sure Wendy probably knows about Jocelyn Bell, who was overlooked in principle for the Nobel Prize for the discovery of pulsars. That was the first that went to Anthony Hewitt, was the first Nobel Prize in astrophysics. And of course, now we just had the announcement in October that the Nobel Prize went for black hole astrophysics. And so that was very exciting, the discovery of supermassive black holes. But the other really cool piece of history I want to mention was about Henrietta Leavitt. That was just a phenomenal story. It's not just her. So she was a member of a group of women that were called Pickering's Harem, unceremoniously called Pickering's Harem. Charles Pickering was the director of the Harvard Observatory at the time, and he had a bunch of male astronomers working for him, and he got so fed up with them that at one point he said, my Scottish maid could do a better job. And he fired them all, so the story goes. I actually am not a historian, so I'm not sure this is exactly it. And he hired his Scottish maid, Wilhelmina Fleming. And Wilhelmina Fleming oversaw Henrietta Leavitt and all of these female astronomers who worked for 25 cents on the dollar. And I mean, they were absolutely impoverished. Some of them had problems like were going deaf. They were,
Henrietta Leavitt did go deaf. Yes.
Henrietta Leavitt went deaf. I mean, it's a tremendous, and the glass plates are stunning that Wendy referenced. And there's this whole history of this Pickering's Harem who collected these glass plates. And I don't know if the Harvard Observatory has retained them because there was some discussion of destroying them because they didn't know how to house them properly. But the history of that story is it's really very moving. And Pickering actually treated these women, I think, with a great deal of respect under the context of the time, right? In the context of the time, he was doing his best. And I think they cared about him very much, but they were frustrated that they were so desperately underpaid that they were actually struggling in total poverty. And some of them were taking care of mothers and children. And but the story, that Davis Sobel wrote a book called The Glass Universe about Pickering's Harem. And it's very interesting. Last thing I'm going to say before I jump, and I let these folks who are actual astronomers talk about data, which I find really exciting to listen to, by the way, even though it's not, I don't touch data. I love hearing about it. The thing that I want to mention about David Sobel and the Glass Universe was that people shouldn't rewrite history in this way. I've noticed that if you now go onto some of the old, like Wikipedia pages, they no longer want to say Pickering's Harem because they find it slightly offensive. And they no longer want to say what Pickering actually said, which was my Scotch maid. But it's very important that we remember these things because we have to understand the reality of what the context was and how tremendous it was that Henrietta Leavitt did what she did and how important it was that Hubble used that and used the science and that exactly that plate that you described, Brian, where he crosses out nova and he puts in VAR, exclamation point. That's the epiphany. So there you have it. There you have it.
Yeah, actually, Dave has agreed to come on my show and into the Impossible podcast. I just want to say one more thing about Shapley, because I think there was a human element. He was the director. Curtis was the director of the Allegheny Observatory, which is part of the University of Pittsburgh. And then Shapley was at Mount Wilson, where Hubble made the measurements that would later, cast doubt upon what the claims that Shapley made and basically turn in favor of Curtis. But actually, I read that he was almost angling for a job of becoming the director of Harvard College Observatory. That was why
he looked at the debate as his job interview talk.
Yes. So Wendy, can you say more about that? Like the human element of it all?
Yeah, well, and there's another aspect of this, which is really fun part of history, which is that, so yes, Shapley was at Mount Wilson where Hubble was, and George Ellery Hale. And there's a story that Alan Sandage actually said to me was true, so I don't think it's just apocryphal. It was that Shapley had photographic plates of the Andromeda galaxy. And one of the really interesting pieces of history was that at that time when Mount Wilson, when the telescopes were being built, there weren't paved roads and there weren't cars when the 60-inch was being built. And they used mule trains to bring up the telescope tube and bring up what they needed to build the telescope. And one of the mule drivers was a man by the name of Milton Humason. And he turned out to be, and I want to say more about Wilhelmina Fleming and Henrietta Leavitt after this too, Janna, because related to this. But he ended up first working as a janitor on the mountain, and then he became an assistant to Shapley and to Hubble. And as the story goes, he was developing photographic plates for Harlow Shapley, looked at the Andromeda galaxy and could swear that he saw variables. And he walked into Harlow Shapley's office and said, "I think there are Cepheids in the Andromeda galaxy." And because Shapley was convinced that that couldn't possibly be true, because that would have meant that that these nebulae were outside this big Milky Way that he was arguing for, he took his handkerchief and rubbed off the places that Humason had marked where the variables were, and lost his chance to make the discovery of extragalactic nebulae. So that.
And then he later hired Celia Payne Gaposchkin. I can never pronounce her name.
Cecilia Payne Gaposchkin. She actually did. She was one of the first women to get a PhD at Harvard. So Henrietta Leavitt and that group of women that Pickering hired, they were not allowed to get degrees at Harvard at that time. And Wilhelmina Fleming had been a high school teacher in Scotland. When she came over, apparently the story is her husband had deserted her. I believe she was pregnant at the time. So she ended up working as Pickering's maid. And he realized this was a woman whose talents were, being totally lost, and hired her. And she turned out to be a superb manager of this group. And people like Henrietta Leavitt and Annie Jump Cannon, I mean, there was just a huge number of women in this harem, as it was called, who did fantastic astronomy, but they were never granted degrees, and they were paid egregious wages, as Janna pointed out. And fortunately, the situation has changed. Wilhelmina Fleming.
I do love that we need to preserve that history, because it's a layered and complicated story, and it really is what launched this field. And I think we have to remember that. And I think we have to remember that scientific integrity, it's really important that Hubble didn't scoff at a woman's work and therefore not use it, right?
Right.
So this
apparently was nominated for a Nobel Prize, but she died. She died before Hubble's discovery of galaxies and before, of course, his discovery of the expansion. She never realized the implications of her own work, which is just sad. She died very early.
Shapley did set up the astronomy department at Harvard so that he could give Cecilia Payne a PhD.
Really?
Wow.
Yeah.
I didn't know that.
Yeah, so the reason Cecilia Payne's she's the first astronomy PhD at Harvard, because the physics department wouldn't give a PhD to a woman.
David, I thought that was also true of Harvard, that the first PhDs were from Pickering harem in astronomy for similar reasons, that they just kind of created a new PhD program to confer PhD. Is that not true, Wendy?
Not true. They were not granted.
I thought one of them, it's not Annie Jump Cannon, I can't remember. Who started the Vassar College Observatory? I'm struggling to remember now. Anyway, I didn't mean to derail the conversation.
no,
It's fascinating. I
fascinating
do
history.
have to go. Speaking, I
Yes.
do have to go, but I'm going to listen on my way out to pick up my children. I'm going to listen, and I want to get back to the data because that's the really great stuff.
Yeah, I want to get to the imaging too. Janna, thank you so much. Congratulations
Thanks,
again on the
Brian.
publication of Black Hole Survival Guide. It's one of our gifts we'll be giving away. There's still time to register for the giveaway. I'll put the link in the thing. And while you're at it, exercise your finger. I always say, make sure those finger muscles are working, and subscribe to the channel. Hit the notification bell if you would, and you will get access to more great content. Like you heard, I'm going to have David Sobel. I'm going to have Sheldon Glashow on the show next week, and Lenny Suskind, and many other people, in addition to all these wonderful guests that I've had on so far. So let's keep going. I want to get to data. I want to get to imaging. Bye, Janna. Thank you so much. Congrats again on an awesome, awesome book. I want to go to our Wyoming Stargazers who are snow gazing tonight. And they graciously sent us some images of what the capabilities of their observatory is able to make. And I want to zoom in here. So we'll start with this. Hopefully this video will play. I don't know, Sam, is this a video I'm going to try to play?
It's a YouTube video, yeah.
It's a YouTube video. Okay. So it's going to ask me to link to a YouTube video. Okay. Well, I don't know if I can actually get that going and not lose the stream here. But I want to look at ask Mike to describe some of these images that are shown here. There's Hubble images, and they're shown next to images made from Wyoming Stargazing. And obviously, Hubble has certain advantages, but it is true that we can do an awful lot from the ground, and we will have some examples of citizen science that people can participate in if they're interested. So, Mike, can you talk a little bit about the facilities at your observatory that we're looking at?
Okay, yes. These pictures were not taken by I didn't take these pictures. The ones that are going to come later are, but my observatory, which is in Jackson Hole, has 3 telescopes in it, one of which is a 20-inch plane wave telescope, and these pictures are in fact taken by the 20-inch plane wave. I also have a 6-inch Takahashi refractor, and I have a 12.5-inch plane wave. And I use these telescopes depending on the object. If the object is a small object, like for example the Pillars of Creation, which we're looking at here, I would use the 20-inch. But for example, the Andromeda is nebula galaxy, is quite large, and it's about 6 moon diameters in size. That's where the 6-inch telescope comes into play because it has a much larger field of view. And then for the moon and the sun and planetary nebula, planetary observing, I use my 12.5-inch telescope, and they are all in the same observatory. Right now, they're getting snowed on outside, but we had a great summer here and a lot of beautiful nights before the smoke from California came in. Now, we are definitely plagued by the atmosphere. Samuel, you were going to also talk about some of those, I don't know which we want to start with, the planetary pictures or these deep space pictures.
Let's go to
either one.
Yeah, let's look at the nebulae, and then I want to get back to some of the discussion that we had. But first, actually, let's look at the Juno image. I want to talk about that. I want Sarah to jump in here with some commentary on opportunities for citizen science, as Mike's doing here. But first, Mike, can you tell us a little bit about the JunoCam images that you're showing here that you processed? You didn't take these. These aren't taken from Wyoming.
No, I didn't. I certainly didn't take them. But the JunoCam project on the Juno satellite was really left to amateurs to process the pictures. The cameras was taking these raw pictures and was left to amateurs. And I being an amateur, I was fascinated by some of the pictures other folks had done. And I put together these pictures. Like the one on the left actually has won an award in Wikimedia as one of the 5 best science photographs, images of the year. It's of the South Pole, and it's a composite of pictures that was taken during the 1st, 3rd, and 4th of the orbits that the Juno satellite made. And it was complicated because there wasn't a lot of overlap between the pictures, so I had to do a lot of hand work to make that picture. The one on the right was taken during the 18th orbit, and it involved 4 separate pictures taken at different distances from the planet. So it was quite a job assembling them into a single picture, because I had to correct for the difference in the distances. But they both came out beautifully, and it just, of course, the satellite is quite close compared to even the Hubble. There's resolution here in these pictures that are beyond even the Hubble images, because the satellite gets as close as several thousand miles to Jupiter when it's at its closest. Now, when it's passing over the pole, like on the left picture, it's about 100,000 kilometers away. The one on the right, on the average, it changed during the 4 pictures I had to use, but on the average, it was about 27,000 kilometers away, taken from a direction, taken from 40 degrees south. So you can see the giant red spot on the upper corner, and you can see some of the same parts of the image that we're seeing on the left at the very bottom. So you're seeing the south polar region as well.
Mm-hmm. Now, Sara, can you talk about, there's, I found online, the American Association of Variable Star Observers has a link to opportunities for folks to help with analyzing TESS data. Can you talk a little bit about opportunities for people that might be listening to get involved with actual research conducted by professional astronomers?
Yes, actually, you can also Google on planethunters.org, and it will relink you to a website for crowdsourcing.
Oh, wow.
And what the mission does is the people who organize this, they take TESS public data and they chop it up into pieces, and you can train yourself on a tutorial on how to find planets by the transit method. And it's actually highly successful. Every year there's a few maybe planets found by crowdsourcing that the professionals missed.
Oh, wow. Yes, I'll have a link to that in the comments in just a second. Really good. Okay, so let's look at one more slide here from Mike's images, and then we'll get back to some great debates. But I do want to talk a little bit about novae and so forth. So we lost our black hole expert, but I want to talk about these images, and as well as what they may portend for settling these future great debates. If we have opportunities, I'd like to know, actually, since we still have Sara's attention, can you talk about the next, upcoming missions that you're involved with, building on the TESS legacy, first of all?
There's so many missions. My favorite mission is actually this. I'm leading a concept study on a mission to Venus, where we would look directly for signs of life and for life itself. We have a small, medium, and large mission we're studying. Small, we're going to partner with Rocket Lab, who are planning to go to Venus. They already have funds and plans to send a small rocket to Venus, which would have a very small payload, and we're helping choose the science instrument. But back to exoplanets, everyone's waiting for the James Webb Space Telescope to launch. In fact, proposals for the first cycle are due in a couple of weeks. And I bet every exoplanet astronomer is working hard. We want to study planet atmospheres, and it's going to be big.
David, can you say more about what James Webb will do and what its prospects for launch and so forth, the challenges thereof?
Well, James Webb is the most complicated, in many ways, engineering and science project ever launched. It's this incredible telescope that will be much larger than Hubble, and because it operates in the infrared, able to stare much deeper in the sky. And I think it's going to have significant impact on many of the questions we've talked about. Wendy could say more about this, but for things like tip of the red giant branch, the fact that you've got a powerful telescope observing in the red, or the infrared, that has much higher resolution than Hubble will enable us to use those techniques to go much further out. And that may be one of the things that, I think for this Hubble discrepancy, it is having new types of data is going to be the way we'll make progress and help. Then one of the things JWST will give us is new types of data. I think it'll also have an enormous impact on our study of planetary atmospheres. Sara Seager spoke of the TESS mission, and TESS is finding planets that transit in front of their host stars. Those planets will be targets for the James Webb Space Telescope that will be able to observe basically sort of before and during and after images. So you'll watch the spectrum of the star before, as the planet moves in front, and afterwards. And that will enable the detection of the properties of atmospheres around other planets, around other stars. Mm. So that's among the things we're all excited about with the James Webb Space Telescope.
Yeah, I was just browsing the guaranteed time observer projects today. Like if you have built an instrument or have some other special role, you get time like guaranteed for you. You don't have to propose actually. And there's so many transiting planets already in those lists. So we'll be seeing results, probably among some of the earliest results we might hear about are about transiting planets.
Oh, it's really exciting.
Yeah, I think every time we made real progress, it has been jumps in our technology. The technology has improved. These things, I mean, we saw it with the debate in the Hubble constant last time. Then you get above the Earth's atmosphere and you suddenly have this capability you didn't have before, and you make real progress. And I think, yeah, we're really looking forward to a new instrument that's sensitive to the infrared and has higher resolution, because we will be able to push farther out with the tip of the red giant wrench. Really,
so I have so we have about 10 minutes left, and I do want to get to questions, but Adam sent me some fresh data. This is fresh data and has plots from
have a very out of date plot there before, which this is a compilation. I didn't do this, but this was a paper last week. So this sort of shows the most recent measurements, maybe in the last 2 years or so. And what is labeled here as indirect is what David was referring to. Observations from the cosmic microwave background and the cosmological model used to predict the value of the Hubble constant. And that kind of peach orange looking band is sort of where those measurements prefer. And then below the dotted line is the direct. And so those are the local measurements and the various techniques that we've discussed in this, the Cepheids, the tip of the red giant branch, Myras, Masers, Tully-Fisher. And I mean, you could see the issue here really quite clearly, I think, is that there seems to be an offset between these two sets of things. It doesn't really look like the direct measurements are drawn from that peachy kind of band. And certainly there are some variations, there's some noise here. But you know, as we try to make this comparison and convince ourselves we really understand the universe from the beginning to the end, you know, this is not a very convincing result of that. So certainly, you know, more measurements and better techniques. But, you know, as I was saying before, it'd be really valuable if people have specific ideas of what is in common with the measurements, either on the direct side or the indirect side, that could cause one group to shift with respect to the other. I mean, you know, we could always sort of pick our favorite measurements, but, you know, that doesn't really give us a working hypothesis of what produces this difference we see. I don't know if and David, the Beerer lensing measurement is at the bottom there. So I think that's the one you were referring to. But I don't know, David, if you have an idea of like what could be in common with these, that could be a systematic even.
I mean, the things that I've looked at most are the lensing, and I was really pleased on these measurements to see the Beerer analysis, which I think is superior and does include the uncertainties in the mass profile. And what are the assumptions we make in the indirect ones? And we've been looking very closely at things like neutrino interactions, and one of the interesting features that has, it makes clear predictions about what the microwave background fluctuation should look like on small angular scales. So we're right now doing an analysis where we're taking the data we've measured from Chile and asking, could we change our cosmological model? And in doing so, shift where that peach curve would be, because all of those techniques assume we know the length of the ruler. So if we can change the length of the ruler, that's the way we would shift the peach curve. I think on the purple curve, with tip of the red giant branch numbers, lie somewhat in the middle. And with Cepheids, I mean, I think our best hope is if we have with James Webb, we will have more data, higher quality data, and we'll either confirm those numbers and the error bars will get smaller, or we might discover something new about their properties or some subtle effect that we've missed in the past.
One of the exciting missions that we haven't mentioned really that actually relates quite directly to this is a European mission called Gaia, which is measuring the parallaxes of billions of stars, and in particular is measuring the parallaxes of some of these star types that we use to measure distances. And so Gaia is due to have their data release 3 in 3 weeks, I think. That will be a very exciting moment because that could give us the kind of precision that we need to truly reach a 1% measurement locally in the direct measurements of the Hubble constant. One never knows what to expect, when a new data release comes out from a new facility, how it will recalibrate things. But that is certainly something to keep an eye on.
One of the cool things Gaia did was I mentioned early on this von Manen result. That was an attempt to measure the distance to Andromeda by looking at its rotation. And von Manen got it wrong, but Gaia had the precision to finally be able to measure that effect at that distance. And so
rotational parallax?
Rotational parallax. Not at the precision needed to really tell us something about this question, but it's kind of cool that it took 100 years to do the von Manen measurement right.
Well, that's where Curtis was right. He just didn't believe that von Manen could make a measurement that small. But Curtis was actually wrong because he didn't believe that Cepheids could be used to measure distances. So there were a lot of who won that debate. They both won in some ways and lost in other ways, which I think is a good lesson for the present.
I also wanted to jump in and defend one other aspect of Hubble's original measurements. We talked about some kind of systematic errors. There were also 2 generations of stars, so-called Pop 1 and Pop 2 stars, and not realizing that fact, but actually calibrating the luminosity of one type locally and then observing the other type far away and not realizing those were actually 2 different types of stars. That led to
those populations, right? So one of our viewers is asking what makes them pulse in the first place, and then what makes them the 2 different populations of Cepheids pulse at different properties.
Right. Well, so Cepheids, like all stars, have an exquisite balance between gravity crushing the star and a kind of thermal pressure, all the heat from the star pushing back, and that's called hydrostatic equilibrium. Normally, a star sits right there in that perfect balance, but there are mechanisms in stars, in particular in their atmospheres, that cause stars to overshoot that. Sort of like, a kid sitting on a swing can sit happily, at the bottom of the swing, but given a little push, will go back and forth. And in the case of the Cepheid variables, there's an element of their atmosphere that causes a greater opacity and can push, like somebody pushing on the kid's swing, that star to become a little bit bigger. And then at that point, gravity starts to win as the star cools off, and then it shrinks again, and then it overshoots. So it's a kind of instability that causes this constant overshooting around equilibrium.
And then the 2 different populations that he was unaware of, or they
right? So that in the first generation there was not a lot of what astronomers call metals, which really just means anything heavier than hydrogen or helium, and so stars had a somewhat different composition. Then once a generation of stars was able to fuse heavier elements in its core and then spew those elements out into space through supernova explosions, gravity sweeps up those heavier elements, and the next generation of stars, still mostly made of hydrogen, but now have trace amounts of these heavier elements, and it can subtly change the properties of stars. It can change their luminosities and colors a little bit. So those are things that astronomers now know and calibrate, but did not know back in Hubble's time.
And these other population of stars are actually lower mass and older stars than the population 2 Cepheids. So they're less luminous. They're a completely different beast.
Wendy, someone's asking you in the chat room about our tip of the red giant branch star is more immune to certain types of systematic errors intrinsically, not by virtue of the fact they're on the outskirts of the galaxy.
Yeah, I think there are some reasons that they are. I think they're simpler in the sense that, as I mentioned, they don't get brighter than a certain luminosity. And so these are stars, their solar mass or so, when they exhaust the hydrogen in their core, and then they begin to collapse, the central parts of these stars become degenerate. They're supported by electron degeneracy pressure. And then they have a hydrogen burning shell. And the stars ascend what we call the red giant branch. Temperature is increasing until it reaches about 100 million degrees. And then you have enough, so that then you can start to burn helium stably. And the star, the degeneracy is lifted, the star no longer is at that luminosity, it rearranges itself and falls onto what we call the horizontal branch. And so the physics of that is very well understood, and people have been modeling that for decades. It's extremely well understood. Physics, all the models predict this. And so we don't have to worry about pulsating atmospheres. The metallicity of these stars that we've been talking about, any elements that are heavier than hydrogen and helium, are reflected directly in the temperature or the color of the stars that we observe. With the Cepheids, Adam mentioned before that we can make corrections for the metallicity, and this is something that, in fact, I and a collaborator, Barry Medor, devised very early on, was to look at the abundances in the gas near the Cepheids. Cepheids are too faint to measure their abundances directly. You have to get spectra to measure their abundances. So it's a proxy. It's not a direct measure of the metal abundance. Whereas for the red giant branch stars, we measure the color, 2 filters, that's all we need, and we know what the metallicity is. It's a one-to-one correspondence. We know what the luminosity is, we know what the metallicity is, and we don't have to worry about pulsations. When we're out of the halo, we don't have to worry about dust. And so I think there are many reasons that they're less complicated. And what still concerns me about the Cepheids is, yes, we can make corrections for reddening. And that's something, in fact, I did in my PhD thesis when we first were able to get CCD detectors and get multi-wavelength photometry. And then ultimately with 2-dimensional infrared detectors to go out into the infrared. You can measure the extinction really well. But the worry is, because of this difficulty, when the stars are in the centers or in the disks of galaxies, it's hard to measure their brightnesses as you're pushing farther out in distance. So you've got potentially the stars are being crowded and blended with other stars, particularly in the infrared. And the sort of nasty part of this is it's the red giants that are doing the crowding and blending as you go to the infrared. So you're trying to simultaneously correct for the metallicity, which may or may not be reflected by the young gas phase, trying to correct for the reddening, and trying to correct or at least estimate what the crowding effects are. So you have to do this as a system, and maybe each of these effects is only 1% or so, but maybe together collectively they're a bigger effect than you think. So
I gotta jump in here and defend
the things that keep me awake at night, and why we started to measure the tip of the red giant branch stars is you won't get to the bottom of these kinds of effects doing one type of measurement alone. So the Cepheids are what they are, but we're pushing them out. So, you know, Hubble increased our resolution, but the farther out you go, you lose that advantage of the resolution of Hubble. So that's why I think we need to take the next jump.
I gotta jump in here and defend the Cepheids. So I think the elegance of the Cepheids is, you know, every individual Cepheid gives you a distance. And so when we look in a distant galaxy, we don't just get the distance to the galaxy, we get many hundreds of measurements of the distance. And so you get to check this sort of internal consistency. You know, one of the challenges, I think, really of the tip of the red
also for the red giant, right?
is
you get hundreds of stars.
With the tip of the red giant branch is there is no such thing as a star that is the tip of the red giant branch. It's a feature, a break in the luminosity of many stars. And so you have to correctly measure where that break is. You don't get a cross check. you don't get many measurements. You just get sort of one shot at that. And, when you
No, look
you
have many measurements. You have many measurements of these stars.
So it's very difficult to actually see, have I properly measured the break, or have I measured a kind of ripple in the luminosity function? And so I think that, as we, are able to move to the near infrared, particularly for Cepheids, to get through the dust and observe many of them, I think we've gotten very clean measurements. At this point, I think, it's hard to beat Cepheids in terms of their range and their repeatability.
Wendy, do you want to respond to that? And then
slightly disagree with you, Adam, in the sense that we have hundreds of stars, in some cases thousands, that define the tip. And so,
but you don't get the tip from any one of those stars. You have to look at all of them and just get one number from that.
Yeah. So we got to wrap up because YouTube is closing down on us. Actually, at one point they had a warning, and it said, "Go to Wikipedia if you're concerned about flat Earth debates." So, we can agree on a flat universe. Yeah, we're being shadow banned. But I want to ask all of you in the remaining precious moments that I have with my friends and colleagues. We'll start with Sara. What not in your field are you most interested in discovering? If you can come back in 100 years, or you keep taking your vitamins, and you live to be 100 years older, when you come back in the 200th anniversary of the Great Debate, what thing will you most want to know if you're coming out of suspended animation? What other, outside of your own field, what would you like to know most of all in 100 years?
Well, I think mine would be pretty simple. I'd like us to have images of the very first objects that formed in the universe. The James Webb is supposed to see back to first light. I don't know if it will, but I think I'd love to just know what really happened in an image, not in inferred information.
Very nice. And let's go to David. What would you like to know most of all outside of your particular field of expertise? What fact would you most like to know in the year 2120?
Are we alone? Are we alone in the universe?
Fascinating. Great. How about you, Adam? Outside of your field, outside of the very fascinating subjects that you study, what do you most want to know?
Yeah, well, I would like to know what dark energy is. We haven't talked too much about that, but that is extremely interesting. I had a second on my mind also to know what LIGO, the gravitational wave facilities, actually what the census of the universe in the dark sort of yields. Very interested in that.
And Wendy, what about you? What outside of your field would you most be curious to know the answer to in the year 2120?
Yeah, I think I'd have to say too, I'd like unambiguous evidence. Is there life elsewhere? And I think that's going to be a fascinating field to break open.
Thanks. And then Sam and Mike.
Not just bacterial life.
Yeah, not slime mold. You want Bach, not bacteria. Sam Singer, director of the Wyoming Stargazing Association. Thank you for sharing your time. What would you most like to know the answer to outside of your field of expertise?
I'm with David and Wendy. Not just the detection of one form of life, but how many intelligent civilizations are out there.
And Michael, last but not least, thank you so much for sharing your images. What would you be most curious to know the answer to in the year 2120?
Well, I'd like to know the answer to this debate, for one thing, because this debate is fantastic, has been very interesting. And also, what is dark matter? What is dark energy?
Very good. Well, I do want to thank all my illustrious guests. I thank you so much on behalf of me, my audience, etc. I want to remind you all to please subscribe to my channel, Dr. Brian Keating on YouTube, but also to subscribe to the Wyoming Stargazing Association's channel. We're trying to get them over the 100 subscriber mark tonight. So hopefully people can do that. I put that link also in the chat. Sign up for the giveaways so that you may too win a copy of either Janna Levin's new book, Black Hole Survival Guide, Sara Seager's wonderful book, which she promised to come on the Into the Impossible podcast for a solo episode, The Smallest Lights in the Universe, Losing the Nobel Prize, which you can get anywhere books are discarded. Adam Riess signed copy of the paper that brought him a good
Better not show up on eBay.
Yeah, I better not. Well, I want to see who got more, you or Wendy, because Wendy's lovely paper, the Hubble Key Project, is also signed and available. two guests will win one of these, or there's two people win each one of these, one copy of each of these books. David, you're going to send me a beer cozy. You promised that you signed, or something like that. Something else that's cozy, maybe. I want to thank everybody so much. This has been so spectacular. I hope we can do it again in 100 years. But even before then, I hope we can all get together. We should be well and enjoy many great debates like this. In contradistinction to the political debates, these are done with great comity and comedy. And I had a wonderful time. I can't thank you all enough. Have a wonderful evening. Good night.
Thank you, Brian.
From the